So I will, let's start. Barış Hocam, are you ready to?
Yes, Hocam, I can
start because you already started yesterday. You need no introduction.
Yes.
Already famous for the little group. Okay, so let's start.
Okay, I can start sharing my screen maybe.
So if you want to make it more interactive, you may also type, I think if it is okay with Barış Hocam, you can also type your questions and we can actually ask them as we go on if you prefer, or would you like to answer them all at the end?
It doesn't matter, Hocam.
It doesn't matter.
Whichever the audience prefers, I'm fine with.
Okay, so just if it is an urgent question that you have to answer right away,
yes,
urgent, so please let me know. I'll interrupt Barış Hocam and ask the question.
Sure. I have the chat open in front of me, so I mean,
you can of course, I can see that, but
okay.
if you don't want to track it, that's also good. Okay, great. So please, floor is yours.
Okay, thanks a lot. So welcome everyone again for this second lecture of
landscape, please.
Landscape. Okay, sure. Okay. So welcome to this second part of this quantum control and its energetic cost discussions. So let me start by simply correcting one thing that I wrote in a wrong way at the end of the last lecture. So obviously the counter-diabatic Hamiltonian that makes sure that cancel this this problematic term here and makes sure that we remain in the adiabatic limit or at all times is obviously not given like this. So this is just a number basically. So we need a Hamiltonian. The actual thing is basically quite a lot like this, but I need to have one M here and then one N here. So sorry for this, I basically wrote it wrong. Maybe I can rewrite it all together so that we have a more clear way. So I have an outer product of N, H dot here, the time derivative of the Hamiltonian, N, and an outer product of N here. So, and then I have an En minus Em. Remember that these N's and M's and this set of eigenvectors and eigenvalues, they are just the instantaneous eigenvalues and eigenvectors of the Hamiltonian that is basically changing in time. So that's the last thing that I mentioned. This is one of the problems of this approach in the sense that in order to apply this to a many-body Hamiltonian, we need to diagonalize the Hamiltonian at every time step. Therefore, it would be quite problematic to do that. So there are other approaches to deal with many-body systems. However, this approach works extremely fine if you are dealing with a single two-level system, single qubit. Even two qubits are, for two qubits, it works quite nice. For harmonic oscillator, it also works nice. I will talk about, I'll give a homework basically related with the harmonic oscillator. And then what it makes is that, as we said, so you have your original Hamiltonian, whatever it is. And if you want to make a shortcut to adiabaticity using this method, using counter-diabatic driving, you basically take your original Hamiltonian and add this counter-diabatic Hamiltonian, which the general form is given like this. And this counter-diabatic Hamiltonian basically makes sure that you remain, you follow the adiabatic adiabatic states, adiabatic manifold, adiabatic path at all times, no matter how fast your Hamiltonian is changing. Okay, this is actually a quite, I mean, maybe not remarkable for me, but maybe for some others, not remarkable, but it's quite nice. So this term is basically introduced by, actually in another context, it's introduced by Demir-Plak and Rice. in 2003 and 2005. So they were dealing with some adiabatic passage problems. So that's the first time that they came up with this expression, so 2003, and also in another paper in 2005, after realizing that this has an effect like keeping us in the adiabatic limit at all times. But then Michael Berry stepped in and made this a bit famous, I would say. So Michael Berry is the Berry of the Berry phase. So he's quite famous physicist. So we have the Berry 2009 Journal of Physics A paper. As I said, all of these papers will be in the folder that I'm going to share with you together with the lecture notes at the after the end of this lecture. So after this, I mean, there are various, there are different problems that we can apply this problem to. One of them, and probably the usual suspect in general, is the okay, the first one is the Landau-Zenner model, which has an avoided crossing. I will explain it to you in a moment. And the other one is obviously a driven harmonic oscillator. And then by a driven harmonic oscillator, I mean an harmonic oscillator that has a time-dependent frequency. Okay, so let me maybe divide this from here, and then let me talk about the Landau-Zenner model. Okay, so Landau-Zenner model is basically, so the Hamiltonian describing this model is something like this. Let me maybe write the Hamiltonian first and try to explain what's going on in this model. So it has a time-dependent Hamiltonian, and it's explicitly given like this. So we have an h bar delta sigma x, okay, and plus I have a time-dependent driving in the sigma z, okay. So I have a g of t that depends on time, okay, and then I have a sigma z here, okay. So if I would like to write this in the matrix form, so the forms of these matrices are given by also Özgür Hoca and Özgür Hoca on Monday, I guess. So sigma x is an off-diagonal matrix that has ones in the off diagonals, and sigma z is the z Pauli matrix, which has a 1 in the upper diagonal and -1 on the lower diagonal. So I mean, if you would like to write this in the matrix form, you can write this as h bar g of t delta minus g of t. Okay. Clearly, we, I mean, in general, we would like to find the eigenenergies and eigenstates of this model. So maybe one homework would be this. So let me express the eigenenergies and eigenstates. So there are, obviously, this is a 2x2 matrix. If you diagonalize this, you would you are going to get two eigenvalues, which are going to be the energies, so E plus minus. So they also depend on time. Let me keep the time dependence for a while again, and then I will maybe drop it for the other calculations for the sake of the convenience of the notation. So E plus minus T is plus minus square root of G of T squared plus delta squared. Okay, and then the eigen functions corresponding to these eigenvalues are as follows. So we have a psi plus, let's say, okay, which can be written like this: cosine theta and sine theta. I will explain what theta is. And we have psi minus. So psi plus is the eigenvector with the eigenenergy, eigenvalue E plus, and psi minus is the eigenvector with the eigenenergy E minus. And then this is given like sine theta minus cosine theta. Okay. So here where I mean tangent theta is equal to something like this: g of t plus square root of delta squared plus g squared t, okay, divided by delta, right? So maybe the first homework would be this. Let's say homework 1, show that theta is expressed in, or can be expressed, let's say, can be expressed in the way given above. Okay. So maybe one hint here is the following. So don't forget to, when you find the eigenvectors, don't forget to normalize them. They obviously need to be need to have a length that's equal to 1. Okay. So maybe not a hint, but okay. Normalize the eigenvectors. The reason why I say this is due to the following: when you normalize the eigenvectors, it would be easier for you to see this form tangent theta being equal to this quantity. Okay, fine. Now, what's going on here is the following. So if you look at the energy eigenvalues here, so we have two energy eigenvalues. If I try to like somehow plot them as a function of time, let's say, or maybe let me first give an expression for g of t, if you like. Okay, so this g of t is the parameter in the Hamiltonian that we are basically changing. We are, in some sense, driving. Therefore, I mean, it can have a general form. Okay, but let's say that we have the following form for g of t. Say g of t is a linear ramp. Okay, so we are changing the value of g from an initial value to a final value. Okay, so let's say that we are changing it from g0 to a value, let's say gd times t divided by tau. Okay, tau is the duration of the process. Okay, so where tau is the driving time. Okay, so this means that we are changing g from g0 to g plus t. Okay, I mean, if you like, you can see it from here. So at g at t equals 0 is g0. Okay, and g equals t equals tau is simply g0 plus gd. Okay, so we are changing the energy eigenstates somehow, but they do not cross each other. Okay, now if you try to plot this, if you try to plot the energy eigenvalues, assuming that we have a linear ramp like this, what you are going to see is the following. So we have the energies here, and I have the let's say t divided by tau on the x-axis. So I'm changing t from 0 to tau. Okay, so t divided by tau simply changes from 0 to 1, if you like. Okay, and the two eigenvalues that I have, so we start from an initial g0. So we start from g0 squared plus delta squared square root for the higher energy level, and for the lower energy level, we start from g0 squared plus delta squared square root. So we start from a certain point and then we have the ramp, and then after some point this starts to decrease. This is, let's say, E minus, and E plus basically does the same thing. Okay, and this is E plus as a function of time. Okay, so this this is an avoided crossing. Okay, this is what it's named. So avoided crossing is, I guess, self-explanatory. So these energy eigenstates, energy eigenvalues were starting to converge to each other, but after some point they avoid this crossing of the energy eigenstates, therefore, and then they got separated again. Okay, so this minimum gap here that you see is when G is equal to 0. Okay, so this is delta basically. Okay, so this minimum gap is determined by delta. So if you have it small, remember this term here, we discussed this yesterday. This is the term that was causing the problems for us, in following the adiabatic limit. So if you have a small gap between the energy eigenvalues, in this case we have two, remember, so we have a single difference between them. So when we have the difference between them becoming small, this term that's causing us the problem for us to follow the adiabatic manifold adiabatic path becomes more pronounced, okay, for a fixed time derivative of the Hamiltonian. All right, so we can actually say that this, so as we change G of t during as the time goes by, the region here is going to be problematic. So this is where we expect transitions between instantaneous energy eigenstates. The region around this small gap or the minimum gap is going to be the problematic region for us. Okay, so just keep this in mind, and you will see the direct effect of this gap closing when we talk about the cost of applying this counter-diabatic driving. Okay, now maybe first of all, maybe this may be the second homework, is to basically find the counter-diabatic Hamiltonian that we need to add. So what should be this HCD for this Hamiltonian H, okay, such that when we add this HCD, we do not have transitions between the energy eigenstates. Okay, so don't forget that there is a double summation here. We have a summation over n, and we also have a summation over m. If you like, I should also explicitly write this. So H bar is sum over m and sum over n. Okay, but don't forget that n is not equal to m here in both of these summations. So in this case, n also, n and m, they are the energy eigenvalues and eigenstates, so they run from 1 to 2, both of them, but they cannot be 1 and 1 and 2 and 2 at the same time. So what you basically have is 1, 2 plus 2, 1 combination. Okay, so let's say that homework number 2 is find the HCD, or maybe even let me write this as the Hamiltonian H here as HLZ, Landau-Zenner, okay, for HLZ, okay. If you like, I can basically give a, okay, maybe let me not do this, it would be maybe too obvious, but as I said, you have two eigenstates, m and n are just psi plus and psi minus. So you basically need to consider two terms, one psi plus h dot psi minus plus psi minus h dot psi plus. Okay, so there is going to be two terms that you need to add up, and all of these things are matrices, so you need to be multiplying two matrices. Okay, so if you like, I mean, it's a big hint, if you like, would be HCD equal to IH bar psi plus the time derivative of the Hamiltonian HLZ, if you like, and psi minus, okay, and you divide this by E minus E plus, okay, and the second term that you are going to have is psi minus H dot psi plus, okay, and then you have E plus minus E minus here, okay. So this is basically the term, okay. But let's see what you get. All right. I'll also tell you what you are going to get when you do this calculation here. What I'm going to do, show you what you get by doing a trick that may be that may seem a bit complicated, but actually it's not. So what I'm going to do is that, so as you can see, this expression for the Landau-Renner Hamiltonian in this form, it's in a certain basis. Okay, remember Ceyhun Hoca's lecture. So this is written in the sigma z basis. Okay, basis of this of this matrix Pauli Z. So I can basically rotate this Hamiltonian to a different basis, which it would be the adiabatic basis. Okay, the basis given by these energy eigenstates of the Hamiltonian. Okay, so that rotation, by the way, what I'm doing is a rotating frame transformation. Okay, and that rotation can be done by a unitary operator. Okay, so we can make a rotating frame transformation. You can look it up from quantum mechanics or an open quantum systems book, basically, with U, okay, the unitary operator that you are going to use is going to be basically psi plus vector itself. Remember, psi plus is a vector, and psi minus. Okay, so this would give you the following matrix, 2 by 2 matrix. So this is cosine theta. So remember, psi plus is cosine theta sine theta. Psi minus is sine theta and minus cosine theta. Okay. Now with this U, I can transform the Landau-Renner Hamiltonian written in the regular way, in the sigma z basis. We usually use sigma z basis. I can write. So let's say that we can express this Hamiltonian in the adiabatic basis as follows, using the following transformation. I can take U dagger HLZ U minus IH bar U dagger U dot. Okay. So this is basically the rotating frame transformation. And remember, by the way, if you would like to reproduce this calculation, and I recommend you to do so in general, don't forget that this theta is given, so tangent theta depends on G, okay? So theta itself is a time-dependent variable. So you need to take when you take the time derivative of U, pay attention to that. But what I recommend you to do is that make the calculations keeping theta as theta, but remember that it's time dependent. At the very end, plug in the value for theta, okay? Now, the result that you are going to get, so in the adiabatic basis, this Hamiltonian looks something like this, okay? It looks like h bar g squared t plus delta squared, okay? Sigma z plus h bar theta dot, remember theta is time dependent again, sigma y, all right? Now, we can immediately see the problem from here, what causes the problem from here. So this sigma z, okay, remember sigma z is a diagonal matrix, okay, so it does not couple the energy eigenstates to each other, okay. So when you hit an energy eigenstate with sigma z, it does not project you to the other energy eigenstate, okay, because it's a diagonal matrix. However, sigma y, remember the form of sigma y, maybe it's 0 minus I 0. Okay, so it's an off, it only has off diagonal elements. So these off diagonal elements basically connect the two energy eigenstates. Okay, so obviously this is causing the problem, and this term, as you can see, depends on the rate of change of theta. And the rate of change of theta, remember, the only thing that depends on time in the definition of theta is g of t, okay? If g of t is varying in a fast way, this term is more pronounced. So we are going to have non-adiabatic, we are going to have diabatic excitation. So we want to remain in the adiabatic limit. When we are not in the adiabatic limit, we have diabatic excitations, okay? So if this theta is large, we are going to have this problem. If theta is small, theta dot is small, the time derivative of theta is small, we are basically fine. But now this term that's causing the problem basically tells us, so let me maybe call this term as HD. Okay, HD is causing diabatic transitions. Okay, this is how people refer to these type of transitions. That's why I'm using the terminology like this. So how can we make this term go away? Okay, now remember that we have transformed our Hamiltonian. So we are in the rotate, we made a transformation like U dagger LZ U, okay? So can we add a term to LZ, okay, such that when we transform it with U dagger and U, it would give the negative of this diabatic Hamiltonian, okay? So to cancel this term, we can do the following. Basically, we would like to introduce a HCD, okay, such that when we transform it to the rotating frame, when we apply a U dagger U to it, it would give us minus HD, okay? And then if you basically go, if you do the calculations, so, HCD is going to be what, minus U HD U dagger, right? And then you are going to have minus H theta dot. We know what HD is. HD is here. H bar theta dot sigma y. You have U sigma y U dagger, okay, which would give you the following H bar theta dot sigma y in the sigma z basis, okay, in the original basis. And this explicitly tells you, so let me plug theta dot in. What you get is the following minus h bar. So let me maybe rewrite it here all together. So this HCD is minus h bar. Okay. We have g dot t, the time derivative of the time-dependent parameter, delta 2 delta squared plus g squared. Okay, and we have the sigma y here. Okay. For example, for a single spin, so this is a spin 1/2 particle, okay, and in order to keep this in its, in order to prevent a diabatic excitations, or in order to keep this single spin in its adiabatic path, when we are changing a parameter, we need to apply an external field, an external magnetic field in this case, and since we are talking about the spin, they couple to magnetic fields in the y direction. Okay, so remember we have the we have the Hamiltonian like this. So we have the sigma in the sigma x, we have the minimal gap delta. We are driving along the sigma z direction. So we are changing, let's say, the magnetic field in the z direction. So in order to prevent excitations between energy eigenstates, you need to apply a third field, an external third field in the y direction. Okay, that is directly proportional with how fast you are changing the field. Okay. So this is the field magnitude, and it's inversely proportional with the gap. Okay, this is again what we expect. Remember, the term that's causing the problem is inversely proportional with the energy separation with the other energy eigenstates, and it's directly proportional with how fast you are doing this driving. Okay, if you do it slow enough, you even do not need this term because you will always remain in the adiabatic limit. Okay. Now, fine. So this is one example, one application of the things that we introduced. Now, but the problem is, as you see here, so we have this counter-diabatic term that we need to apply externally. As I said, if you are talking about a spin 1/2 particle, in this case, we need to apply a magnetic field in the y direction. Okay, but this needs to be done externally. Okay, this is what we mean by controlling this quantum system. Okay, if we want to transform this state in a robust manner from an initial state to a final state, or let's say that we would like to remain in the ground state of this model at all times as I change this parameter g. Okay, for example, I would like to stay on this ground state at all times. Okay, I do not want with any probability, I do not want to I do not want any probability of being in the excited state occurring, actually. Okay, so I need to apply this external control. Fine, but this is going to cost me. Okay, energetically, I need to apply a magnetic field. I need this brings in an extra additional energy cost to the picture. Okay, now the question is, what's this energetic cost? Okay, how do we quantify it, and how can we, and how it behaves as we drive this system? Okay, now one approach, so there are multiple approaches for this problem, and there's no single approach to this problem to quantifying costs of these control protocols. But one, and probably the most famous one, is looking at the norm of the Hamiltonian. Okay, so the cost of applying HCD. Okay, so let's denote it by, let's say, C. Okay, so one way of quantifying this cost is as follows. So we integrate from 0 to the duration of the driving, tau. Remember, the process takes tau amount of time. The norm, norm of HCD. Okay, and since this is also dependent on time, this may also be dependent on time, dt. Okay, as I said, this is one way of quantifying the cost, and then the average power that you put in to this control, okay, or the instant. So this is the total cost, or maybe let me. So this is the total cost. Is something like this. By the way, let me also, one second. Let me also define what this norm is. This is basically, they are multiple ways of calling these, but we are using just the trace norm, okay? So trace norm is basically, so the trace norm of A that we use here is actually the trace of the square root of A dagger. Okay. Or was it A dagger? Sorry, let me check this. Yeah, it should be, no, A dagger A, excuse me. So it's even square root of the trace of A dagger A, okay? So, but for Hermitian matrices like the one that we have here, it's basically the absolute sum of the energy eigenvalues. So Özgür Hocam, I have a question.
Yes, so what's the unit of this C? Is it joule second?
Yes, it should be joule second. But the instantaneous cost or the average power usually is more intuitive in this sense. So let me maybe also talk about that. Instantaneous cost. So let's say that the average power, or okay, let's say just the instantaneous cost. So maybe del T of cost is basically scales with the norm of the counterderivative term. Okay. So actually you can easily calculate this. By the way, let me write this here. So for Hermitian operators, this norm is, by the way, trace norm. This is trace norm. Maybe let me write the name for future reference. Trace norm, this object is just the sum of the absolute value of the eigenvalues. Okay. So this is basically how we define the cost in general. As I said, there are other ways of doing this, but this is the probably the most famous and the easiest one to calculate. Now, if you, I mean, we can basically calculate this term, okay, for the Landau-Zenner model that we are talking about, okay. So what we get actually in this case would be the following for the Landau-Zenner model. So let me look at the instantaneous cost, okay. So for the Landau-Zenner model, del TC is equal to 1/2 absolute value of G dot times delta divided by G squared plus delta squared, okay? So this is in general what you get as the cost of this driving, the energetic cost of this driving, at least instantaneous energetic cost of this driving, okay? Now, maybe what I can do is that I can show you how, okay, there is one, G of T fonksiyonu tam olarak ne? G of T is a time-dependent function that we use to change this term in the Hamiltonian, which basically controls the energy gap between the eigenvalues. Lambda G çarpanıyla alakası yok. So this is our Hamiltonian. This is a time-dependent Hamiltonian, and G is the parameter that we are changing as a function of time. Okay, and as we change this G from a certain value to a final value, the energy levels of this Hamiltonian closes up, and then they again open up. Okay, so if you consider this G of T to be this linear ramp, okay, so at T equals 0, you start at G0, and at T equals tau, you arrive at G0 plus G0 plus GD, okay? And in the meantime, you cross a point where G is basically 0, and then in that case, the energy level separation is at its minimum, okay? Fine, just let me try to show you this. Let me try to show you how this cost scales. Okay, I guess you can see my screen at this point. Now, this is the counter-diabatic Hamiltonian that we have, as I told you. Let's say our driving time tau is 1. Maybe even I can enlarge this a bit, if you like. Okay, this is better, I guess. So let's say that our driving time tau is 1, okay? So the whole process of changing G from an initial value to a final value takes tau equals 1 in arbitrary units, okay? So we calculate the norm of this counter-diabatic Hamiltonian. So this norm 1, this is Mathematica, by the way. I recommend you to use this when you are doing calculations. You can do symbolic calculations also. If you want to pursue further things in physics like master's, PhD, you would eventually encounter using Mathematica at some point. So, okay, let's say that our total duration of the process is 1. So this norm 1 corresponds to the trace norm that we want to use. And then I picked a couple of parameters for you. Okay, so this is the time derivative. This is G dot GD. So G0 disappears. I put GD to be 0.4. So we start and so this is G0 actually, if you like. Let me put this. Sorry, this is full G. G0 is minus 0.2. So I'm changing G from minus 0.2 to plus 0.2. Okay. And then I set the minimum gap to be 0.1. All right. And then I calculate this cost, and then I plot the cost. This is the instantaneous cost. Okay. I plot this cost as a function of time. All right. So this is what I get. Okay. As you can see, in the midway, so this horizontal axis is the time and vertical is the cost. Okay. So this instantaneous cost makes a peak when we actually have G equal to 0. So this is right at T equals 0.5. And if you put T equals 0.5 when tau is equal to 1, okay, what you get is G to be is 0. Okay. So we are at the minimal gap point. Okay. So when we are right at the minimal gap, the instantaneous cost makes a maximum. Okay. The reason for this is that is the part that's the hardest to go over. Okay. If we do not control that part in the time evolution, we would basically get a lot of unwanted excitations that we want to suppress. Okay. Therefore, the cost that we have, the instantaneous cost that we have, is maximum right when we are at the minimal energy gap. Okay. So if you increase the driving time, so let's say that we complete the process at tau equals, not tau in tau equals 1, but tau equals 10. Okay. So we have a longer process, which means that we are more slowly changing the function G. Okay. Let's see what happens in this case. Then we need to plot this from 0 to T equals 10, obviously. So you see the same behavior, but as you can see, the magnitude of the cost dropped by a factor of 10. Okay. The reason for this is that since we are more slowly changing the parameter in our Hamiltonian, the costs dropped. Why? Because we are more closer to the adiabatic limit in this case. So for example, if you even make this higher, what you are going to get is even lower. So we increased by a factor of 10, the cost dropped by a factor of 10. Okay. So this is well within the adiabatic approximation. So if you do things slower, you have reduced costs basically. Özgür Hocam, bir şey.
Yeah, this is a bit confusing for me, but because if I keep my magnetic field plugged in for a longer time, I will pay more electric bills, no? So this is somewhat intuitively unclear.
Okay, fine, I understand, but this is not the total cost. So I'm not integrating over the total. So the total cost will be the area underneath this curve. This is the instantaneous cost, basically.
So probably overall the cost will be higher, yeah, if you go slower.
Yeah, I mean, probably, but the thing is the magnitude of the field is also decreasing as you increase the time. We can also check this, but the magnitude of the field that you need to apply when you drive the system in a longer time also goes down. That's also
there is no fundamental law that cost will be constant, no?
Can you ask again? I couldn't get it.
So there is no fundamental reason why the cost should be the same. So you are just saying that it is non-trivial. Maybe the cost can be lower or higher, right? In the longer term.
I mean, in general, we know that if you go to the adiabatic limit, the cost will be 0, right? Because if you do this infinitely small, you will always remain in the adiabatic limit, and then you do not need a control, an external field to control the system. The only reason why we need this external control is due to the fact that we want to drive the system at a finite time.
Okay, then we expect that the overall cost will be smaller.
Should be smaller, yes.
Okay, okay.
So I mean, if we make this even maybe 10,000, it would be even 2 orders of magnitude smaller than this. So I mean, as we increase tau, the driving time, the total time that we require to complete this process of changing G, the costs will be lower. And the other thing, maybe I can show it to you in very briefly, is the following. So this gap is also important, the minimal gap point. So remember, when tau is equal to 1 and the minimal gap is 0.1, the total cost is around 2, the maximum value. And this is not the total cost, excuse me. The maximum value of the instantaneous cost is around 2. So if I even reduce this gap, the minimal gap between the energy eigenvalues, so if I reduce this like 1 order of magnitude, as you can see, I have an increased cost around that minimal gap point. Okay, so since these two energy eigenvalues are really close to each other, any deviation from the adiabaticity, any deviation from slow variations can easily induce transitions between these energy eigenstates. Okay. So there, again and again, there are 2 important parameters: the energy separation between your the separation between your energy levels. The first one, this is inversely proportional to everything, and then the other problem is how fast you are driving your system. Okay. So the energetic cost of these processes are quite important. Also, so the thermodynamics of quantum control is basically coming from this. How efficient can we make these control processes? Now, once again, let me remind you. So I guess I'm also running out of time a bit. So I started a bit late, but it's also a bit late. So I don't know. Okay, let me maybe do the following. So let me give you a quick tour of papers that use these shortcut methods in different problems. Okay, so in order to do that, I will share one more screen. 1 second. Here. Okay, just 1 second. Sorry. So let me share my full desktop. That would be easier probably. Can I get rid of this? I don't know. Cool. So these are a couple of papers that are applying that are related with these quantum control stuff plus thermodynamics. Okay, so very briefly, let me show you a couple of things. I will group them when I upload them to the drive. But for example, this is one of them. This is a perspective paper. These are, so the first things that I'm going to show to you will be mainly review-like papers, so you can have a general idea of what's going on. So this is a perspective by leaders, really the leaders in the field. It's related, it introduces a couple of different control methods that are thermodynamically efficient, but not the control method that we were talking about throughout these two lecture course. Okay, you can learn new techniques from there. Maybe the first thing that I needed to show to you should be this. This is a huge review paper, like it's 54 pages. It has all the techniques in it, shortcuts to adiabaticity, everything that you need to know.
Could you zoom in a little bit, Barış? So we can...
Yes, Hocam, sure.
Great, thank you.
Maybe it's better than this. Okay. Yeah, I can check it from the tablet also. Okay. So as you can see, there are many methods. If you like, I can maybe show it to you. So this is the only method that we talked about. Okay, this counter-diabatic driving. Now, as you can see, there are other methods. For example, inverse engineering approaches, invariants, adiabatic invariants, variational methods, fast-forward methods, optimal control. These are different methods of controlling quantum systems, okay? All of them have some certain costs, all of them have some advantages, disadvantages, depending on the problem that you would like to solve, okay? This counter-diabatic driving is one of the first one of these guys, at least first popular version of it. Therefore, I wanted to go over this. But as I said, there are many different approaches, and I would, I mean, if you are interested in this, in these things in general, I would recommend you to go over this. This is a bit more technical, beware in general. There's a short, a bit more non-technical version here. So this is a shortcut tour of quantum control methods for modern quantum technology. So these guys also touch on different aspects of these control together with the costs and where you can use them basically for modern quantum technologies in general. Maybe just to show you a couple of different things where you can apply shortcuts to adiabaticity. One of them would be this. So enlarge this. We were talking about, actually, I guess Jane was talking about creating entangled states. For example, efficient generation of triplet Bell state, which is a maximally entangled 2-qubit state between coupled spins using transitionless quantum driving. This transitionless quantum driving is exactly the counter-diabatic driving that we are talking about for these 2 days. So you can use these methods to generate entangled states, etc. They also use optimal control. They basically compare these 2 approaches in generating entangled states, okay? Another probably interesting one would be this. Shortcuts to adiabaticity for quantum annealing. Now let me maybe very, very briefly say a couple of things about quantum annealing. So quantum annealing is a way of doing quantum computation, okay? So while we are talking about quantum annealing, maybe we can also mention adiabatic quantum computing, okay? So this adiabatic quantum computing is an approach in quantum computing, which you do the following. You take an Hamiltonian that you can prepare the ground state easily, okay? Experimentally, you prepare that ground state, whatever it is that you can easily prepare, okay? And then adiabatically, which means, as you all know up to this point, very slowly introduce another term in the Hamiltonian, such that if you do this very slowly, you will be in the adiabatic limit, which means that you will follow, you will always remain in the ground state as you introduce this new term, if you do this adiabatically. So, and then you introduce this new term up to some certain level, I mean, depending on what you would like to solve. And then you find the ground state of that final Hamiltonian in your physical setup, okay? Annealing methods also use similar approaches, but the problem with these type of things is that we can go back to the first part of the first lecture. The problem with these is that these methods they need to be performed adiabatically, which means they need to be performed quite slowly, okay, depending on the energy gaps. But then we don't have that much time, okay? These are quantum systems, they get spoiled, they lose their quantum properties quite fast. Therefore, applying these shortcut methods to these adiabatic quantum computing or quantum annealing methods are also quite interesting. But again, there are a couple of problems. So these annealing problems or adiabatic quantum computing stuff, they usually involve many-body systems, and using, for example, the counter-diabatic driving that we were using in many-body systems is a bit problematic. For example, in this paper, the author uses an inverse engineering approach, which is a bit different method to achieve shortcuts. Okay. What can I say? So while we are talking about quantum computing, I can talk about this paper also. So this is another way, another application of shortcut methods. Okay, this basically uses counter-diabatic driving, but then so in this paper and in a couple of following papers, people introduce ways to map adiabatic quantum computing to circuit model of quantum computing. Okay, so you may, or gate-based quantum computing. Actually, there are 3 ways of doing quantum computing at this point, plus one maybe. Inançhoca will be talking about them. So adiabatic quantum computing, circuit-based or gate-based quantum computing, and measurement-based. Plus there's the topological ones. So using a correspondence between the adiabatic computing and quantum gate-based quantum computing, basically applying the gates through an adiabatic evolution. You can also use counter-diabatic driving in this gate-based quantum computing also. This is for a single qubit, and then there's also another paper here, which I would say, so superadiabatic controlled evolutions and universal quantum computations. Again, shortcut methods, and especially the counter-diabatic driving is used in these cases. Maybe, okay, this is also quite important. A bit more thermodynamics side. By the way, the cost of this shortcuts are also important when you are doing a computation. Remember, we would like our computers to spend less energy and do more computation. This is also true. This is also true for future quantum computers. So you would like
Barış
them
Hocam,
to be.
Barış Hocam, maybe we can say at least that I think we're really running out of time.
Okay, fine, Hocam. I can stop at this point. Yes. So let me stop here, and you can. I will upload this to Drive, and then I will let you know through the chat in the afternoon session. You can click the link. I will send it to chat in the afternoon session. You can click the link and look at the papers in general. Sorry, I'm a bit over time. Thanks a lot again.
Thank you again for a very nice talk. I think there had been some questions, but let's just, if we maybe have time for a very quick one, but.
Okay, I'm wondering, there's one question that I can see. I'm wondering something, if the delta between 2 energy levels goes to 0, how is the adiabatic process at this point? This is a quite nice question. So the thing is, there can be level crossings. Okay, this is possible, and this is so in that case, what happens is the following. So you have one eigenstate. Let's say that we have 2 eigenstates. Okay, so the energy of the lower eigenstate is one thing. The energy of the higher eigenstate is the other. Okay, E plus and E minus. Okay, so the energy levels cross, but the energy eigenstates remain the same. Okay, so when they cross, one of them is now the excited state, the other one is the ground state. Okay, now when you have this crossing, if you really go slow, in that case you basically need to go infinitely slow if there's a level crossing. Okay, if you go infinitely slow, you really stay on the same energy eigenstate that you started with. Okay. What I mean is the following. Let's say that we have an energy level crossing, and before the energy level crossing, I started at the ground state. Okay. And I increased this parameter G. So I approached to the energy level crossing. I'm still at the ground state. And then the crossing occurred. If I do this infinitely slow, I am still at the same energy eigenstate that I started from, okay? But this is not the ground state at this point. So I'm at the excited state. So I will continue following that eigenstate. If you do this infinitely slow, this is basically an adiabatic passage, okay? This has also applications in quantum technology. So you can have population inversion like this. So you start from the ground state, populated fully, and you end up in the excited state, again populated fully.
I think I have to intervene again. I'm very sorry.
Okay.
But maybe what I can do is that I can officially announce the session as over. We're gonna reconvene at 2:30 for Professor Durak's talk. And in the meantime, if you want to stay on and discuss a little bit more, we can actually do that. So please, I think Şevval Hanım and Barış Hocam, so if you want to discuss more, so please,
sure.
You can stay, I think, online. There's no problem. Anybody who else is interested. But if you need to go have lunch and get some energy for the afternoon session, you can do that now. Thank you very much.